So first I want to say hello to everybody. Of course, those on Corfu and all over the world. Because I'm not there, it will be a little bit difficult to have some discussion after the talk. I'm not on the boat trip, for example. So my suggestion is that you just send an email, and then we can also always arrange perhaps for a Skype conversation or something like this. This is the problem because there are no breakout rooms, as far as I understand, in this conference. So let's get started. So this is a workshop rather, and there are many, many talks, and all very advanced talks and very technical and very complicated. And this talk will also be very technical and very complicated. But I want to focus on something very concrete. And in fact, I want to focus on one equation, and that is the following equation. So the master field that I mentioned in the title of the talk is essentially determined by an algebraic equation for D traceless Hermitian matrices A hat of dimension n by n, and this is the equation. And here's A, double commutator, this is something complicated, and this is an inhomogeneous term. Now this P is a homogeneous polynomial of degree K, which increases very much with n, and we'll discuss it later. And for the case we are really interested in, the D is 10 and the F is 1. That means I don't throw this term out. This will become clear later on. Matrix indices run over 1 to big N, and directional indices over 1 to big D. And these P's and these etas are fixed random numbers. These are uniform random, and these are Gaussian. This will become clear a little bit later. And this P is actually what is called the Pfaffian, and we discuss it later. But this is the equation I want to talk about. That equation is quite a challenge for mathematics and for computational science. But that equation is also of interest to physics. Well, why? Because the solution of that equation may contain information about the emergence of space-time and the birth of the universe. So that is of definite interest, that is clear. Now, in this short talk, a relatively short talk, I can only give you some background in an ultra short version, because the main focus of the talk will be on discussing of how we get solutions of this algebraic equation. So that is a very concrete. So this is the equation I want to talk about, and we want to get solutions. But very quickly, I will spend 2 slides and perhaps a few minutes on it to say why this equation may be of interest. So ultra short background is that we start from the 2B matrix model, which reproduces in particular the structure of light cone string field theory of type 2B strings. The 2B matrix model has a finite number of n by n traceless matrices. There are the 10 bosonic matrices, and there are essentially 8 fermionic matrices. Now, in an earlier talk, John Nishimura has already discussed this 2B matrix model, or the IKKT model, in some detail, so that is good that I can be short. Now, the partition function of the 2B matrix model is defined by a path integral, really just an integral over AM psi, with a weight factor, with a bosonic action and a fermionic action. The fermionic matrices appear quadratically and can be integrated out exactly, and then we get this so-called Pfaffian. Now, for strings of bosonic observables, so a series of bosonic observables, the expectation values are defined by the same A integral as I had for my partition function, namely the exponential weight with the bosonic action and this Pfaffian. Now, for large n, these expectation values can also be obtained by inserting matrices A hat of this so-called master field. That idea goes back to Witten. I have some references in the middle of the slides, and that is Witten's Cargès in 1979. So that is definitely a very old idea. And there's a further work by Greenside and Halpern, which I will use shortly. So the idea is that you have these observables, then you just put in the master field matrices and you're done. You don't need to do any integration. And that holds in the leading order of n. Now, excuse me, I go the wrong way. So now recently, I have suggested that precisely this master field matrices of the 2B matrix model may give rise to an emergent classical spacetime. I repeat some of the details in the appendix A of the PDF of this talk, so you can have a look at it, but I don't want to spend more time on it. The point is, I will emphasize this here in words, is that these matrices A and psi of the model are just integration variables. They are gone. What you get out are numbers. And so these numbers, that information is contained in the master field matrix A hat. Now, if you assume that these matrices A hat are known, and if you assume that they are approximately bent diagonal, that has been seen by earlier numerical work, I refer to that in the appendix, then it's relatively easy to extract a discrete set of spacetime points and an interpolating metric G of an interpolating coordinate. It's also possible in principle to get from appropriate distributions of the extracted spacetime points, the metrics of the Minkowski spacetime and the spatially flat Robertson-Walker spacetime. Now, I don't want to say more about it. I gave a sort of semi-comprehensive review in the Epiphany meeting in Krakow in January of this year. But I want to move on. So this was assuming. But we want not to assume things in physics. We want to calculate them. So we want to calculate these master field matrices A hat. And if we want to calculate them, for that we need an equation. So now I can slow down a little bit. I was a little bit fast here. Now the good news, let's start with some good news for a change. The good news is that the master field equation has already been established nearly 40 years ago by Greenside and Halpern, the reference at the end in nuclear physics. This was even before the archive existed, right? And they write in the first line of their abstract the following sentence. So we derive an exact algebraic master equation for the Euclidean master field of any large N matrix theory, including quantum chromodynamics. Now, any means any, and if we are interested in something more than QCD, QCD is very interesting, no question about it. We had actually a rather interesting talk about it yesterday on the matrix model of QCD. But if we want to do something else than QCD, then we can use, instead of any, the large N 2B matrix model of Kawai and collaborators. So if we now build on this work of Greenside and Halpern, then we have the 2B matrix model bosonic master field in what is called a quenched form. And that is this form. That is, this is this master field matrices, directional index mu, KL matrix index 1 to n. And what happens is that there is this behavior of a phase vector that is extracted out. And here I have a matrix A hat that has no dependence, direct further dependence. So the P hat are random constants. I will mention them a few lines below. And this dimensionless time T equilibrium must have a sufficiently large value in order to represent an equilibrium situation. This work is based on this Langevin stochastic quantization procedure. So tau is this fictitious Langevin time, and tau must be large enough. But the tau independent matrix that enters here, this lowercase a hat, that is given by the following algebraic equation. Here there's a term that comes from a derivative with the tau actually. And here we have a drift term, and here is a noise term. So this is in terms of the master momenta p hat, and they are real, uniform, random numbers. And the master noise matrix of the Langevin approach, they are real Gaussian random numbers. Now, and this equation is, of course, precisely the equation 1 that I started with. So that is the sort of meaning. So we are really interested in solving this equation for given random p's, for given random eta. And if we have the A hat, then we have the full master field matrix capital A hat. So the real issue is here this algebraic equation, and that we will now discuss in more detail. So the algebraic equation 1 is actually rather formidable, and for starters it makes sense to consider a simplified equation simply by knocking out this complicated term. We said this F is 0, so the fermions basically are out. And we are left with the PA on the left-hand side, the double commutator. Now this Pfaffian term is removed, and the noise. So the matrices A hat are n by n traceless Hermitian matrices, and the number of variables is d times n squared in leading order, and this grows rapidly with n squared. And what is important to notice is that this equation is essentially a cubic polynomial. You see, this is a cubic term, a linear term, and a constant. Now, this equation, n by n matrix, is impossible to obtain a general analytic solution in terms of arbitrary master constants p hat, eta hat. So what we will do instead is we try to get solutions for an explicit choice or realization of the random master constants. And this is not obvious. So if I consider the case of 2 dimensions and n is 6, very modest, but we have to start small, then the simplified equation that I have here is already an equation for 70 real variables. And then we have a particular realization. Let me call this realization the alpha realization. And other realizations give similar results. Now, specifically, if I want to be very clear and specific on what I give you, I must give you these random numbers, and these are 76 numbers. So what they are is frankly not important, but for honesty, I will give them to you. So here are the p hats, and here are the eta 1 hats, and here are the eta 2 hats. You see lots of numbers. And now the problem is totally well defined. And it is possible to obtain, with some effort, a particular solution of this simplified equation with these pseudo-random constants in the alpha realization. And these solutions, let me call that A hat alpha sol and A hat 2 alpha sol. Now, I'm not bothering you with the numbers that enter in these equations. There are 70 real numbers in there, Hermitian matrix. Let's just consider at the absolute value, and then we have this simple plot, a density plot, and you don't really need to know what it is, but you see there is no clear structure here. So there's no obvious bent diagonal structure. If we now change the basis in order to diagonalize and order the mu is 1 matrix, and this was already also what entered in the talk of Jun Nishimura earlier, even though we work with the Euclidean theory, then we get matrices A prime and A prime 2, A prime 1 and A prime 2. This is now diagonal and ordered. And now let's look at the absolute value of the matrices. Now this is on the diagonal, that is not a surprise. And these are small values and these are large values. They were large negative, they were large positive. Now they are the absolute value. So they go like this. And here we now have, this is the result of the solution, the A prime 2. And it is clear that you see some structure here. So this looks very different than this. I hope you agree with me. If you were sitting in the audience, I could look you in the eyes, and or you can nod your head. You agree that this looks different than that. And now we have a diagonal and a band diagonal structure in the solution. And that is a highly non-trivial result. So this is information that is contained in this solution. You see, the only thing I do is I change the basis. I change nothing. So this is an important result. Now, needless to say, D is 2 and N is 6 are very small. I agree. But 70 is already a big number. But it turns out that more recently, scientists at Google Research have obtained numerical solutions of my simplified equation 3. Now for D is 10, like we want for the 2B matrix model, and N is 50. So that is quite an increase. These involve now something like 25,000 variables. So that's a 25,000 dimensional space. And they get the solutions. And I've been told that these solutions also display the band diagonal structure. That has not yet been published. I heard from this from Thomas Fischbacher. So this really appears to be that this type of structure extends to larger N. We now know from the Google people that this certainly goes to N is 50. So work is in progress. But I have roughly 10 minutes left, and I will make it. But what we first need to make sure of, the Google people are working on this, we need to make sure that dynamical fermions do not spoil the structure. I have really knocked out the effects of dynamical fermions, and now I want to put that in. So we looked at solutions of the full bosonic master field equation. That is the one I really showed you on the first slide, where we set F is 1 to include the dynamic fermions. But first we will do this with small values of D and N. We have to start slowly. And now let's discuss this Pfaffian. This Pfaffian is a case order homogeneous polynomial, which I will denote symbolically by pk. And k, I remind you, is d minus 2 times n squared minus 1. Now, the basic structure of this algebraic equation 1 is really like follows. Here I have a linear term. There I have a cubic term. There I have a term from the variation of the Pfaffian over the Pfaffian. And here was the noise. So these are constants, right? So here enter the eta, there enter the p. If I now multiply this equation by this polynomial, I get a polynomial of order k plus 3. And it has this structure. So the full bosonic equation is a k plus 3 order polynomial. As a start, I've considered the case of n is 3, d is 3, and f is 1, we put in the fermions. And this model still has a supersymmetry invariance. And now we have 8 generators, n squared minus 1, and they are, of course, proportional to the well-known Gell-Mann matrices. And the bosonic matrices are simply expanded in terms of the Gell-Mann generators, where these are real coefficients. Now, the good news, that's why I did this, is that there is an explicit result for the Pfaffian. This was done by work of Kraut, Nicolai, and Staudacher. The reference is given already before 1980, right? And you can write it in the following term with commutators, anti-commutators, and the trace. So it's rather complicated, but you see it is 8 order, 1, 2, 3, 4, 5, 6, 7, 8. So that is the Pfaffian. And the equation is now totally well defined for this case. If we again take an explicit realization of the random constants, then I have established the existence of several solutions of the full bosonic master field equation. For this case, D is 3 and N is 3. And moreover, if you look at it, and if you are optimistic, as I am, and we should all be, then you may even detect a slight band diagonal structure after this diagonalization. But of course, N is 3 is too small for definitive statements. So details are in this paper, I reference later. But we even want to move on. And so the D is 3, N is 3 result was obtained by a direct algebraic calculation. To get further is impossible in this way. But it may be that I can use an indirect numerical approach. And this goes back to the idea which was emphasized to me by Jun Nishimura. He also used that in his papers, is to use the fact that the square of the Pfaffian of a skew-symmetric matrix, curly calligraphic M, equals its determinant. So that is the Pfaffian squared is the determinant. So if I now have the variation of the Pfaffian over the Pfaffian, then this is a half of the variation of the determinant. And that we know, of course, very well from, say, loop calculations or from GR or whatever. That is the trace of M inverse variation of M. And M here is now depending on the master field matrices. And this trace can be evaluated numerically. And this has been used, for example, in the work by Costas et al., including Jun and including Asato, and the references at the end. Now, so I am now solving my algebraic equation, and I have used this approximation. The work is still in progress. And this is the status of what I've achieved by now. So first, the DN33 case. There we have 3 times 8 is 24 variables. This polynomial is really 11 order already. And that I've managed to do numerically and took me about half an hour, this order. Now, what is important, of course, is that I reproduce the previous algebraic results. So this is working. Then, step by step, I go now to D is 10. Then the number of variables is 80. And the order of the polynomial is already 76. So this is terrible. But I could do it. And let's say this took me about 3 days. This order, the calculation took me about 3 days. This gives you the order. This is the order hours. This is the order of days. But what we really want to do is want to move on to 10 dimensions and at least 4 for the matrix size. And for that, I have a preliminary result, for which there's, of course, not time enough to discuss. I will just flash it to you. The point is, this is very interesting, because then the Pfaffian becomes complex. And that means that the solution has complex variables. So these are 150 complex numbers. That means 300 real numbers. So this is now 300 real numbers. The order of the polynomial is 123. And I have managed to get some results. Let me try to skip ahead. I don't know if my shortcut works. Oh, yeah. Hang on. So let me just skip ahead. And for the organizer, don't worry, I'm nearly done. And I get you an approximate solution on page 29. 2 minutes, I guess?
2 minutes.
Okay. So here we are. So the numerical results of the first 2 rows in the table that I could do with the minimized routine of Mathematica. And this uses this downhill simplex method. But this procedure no longer works for 300 real variables, like I'm interested in. And instead, I have made some simple procedure which I was able to parallelize myself. And in this way, I've obtained a numerical solution. Now, let me give you the results directly in my 2 minutes, because I've forgotten to go to the conclusion. So just very quickly, the result. So we get the equation. If I now diagonalize it, so this is the approximate solution. This is what I get with a penalty function of 400. So this is not so good yet. Took me already many, many days to get here. And the point is that I have these approximate solutions with this behavior. And I want to be positive. So there's no clear signal yet for a diagonal bend diagonal structure. But perhaps we see a trend. So let's just look at the A'2 matrix, then it looks like this for this rather poor approximate solution. This is not a bent diagonal. And here it comes, if you are optimistic. And here you see it even better. For the A hat 6, you also have it. So this is a poor penalty, not at all good. And here you see it getting closer to the diagonal. This is for 310 penalty. And this is what I just got a couple of hours ago, 209. This is the structure. Good. Let me get to the conclusions, and then I'm done. So you have to look, what is the page number? I don't know these by. All right, it's page 20. So the conclusions. So it is conceivable that the new physics phase gives rise to classical spacetime, gravity and matter, as described by our current theories of general relativity and the Standard Model. And so there may be a new physics phase. For an explicit calculation, I have turned to this 2B matrix model, which has been proposed as a non-perturbative formulation of type 2B superstring theory. It has to do with empty. Now, the crucial insight is that the emergent classical spacetime may reside in the large N master field A hat of the 2B matrix model. There is the information. In the appendix, I give you the heuristic argument for this. So why the spacetime comes out of here, that is because there is the information. And we now have started to solve the full bosonic master field equation. And first results are in, but it's fair to say that the road ahead is long and arduous. And with that, I thank you for your attention. I will stop the share.
Thank you very much. We have about 3-minute question time. Is there any question here?
Oh, hello, Frans. This is Olaf.
Olaf, you are sitting at Corfu, right?
You had this Pfaffian in your master equation, right?
What did I have?
In your master equation, there was this Pfaffian.
Yeah.
Would it help you to make a change of variables such that that Pfaffian is the Jacobian of your variable transformation?
Perhaps, perhaps not. You see, we will discuss over a glass of wine and on the boat trip about this. It may be, you see, what I learned was that if the equation is ghastly, then real miracles do not occur if you do something what you think is clever. So I will certainly have a look at it. So if you have different coordinates that make the Pfaffian very much simpler, then that would perhaps help me. Yes, I would be interested, Olaf. You must tell me. So for that, you send me a little email and we have direct contact.
Okay, I'll do that. Thank you.
Any other question? Okay, any question online? Ishima-san, please ask question.
Okay, so you're using Greenside-Halpern's formalism, and you said that this master equation works for any large N models, but I still have some doubt that it cannot be applied to the 2V matrix model or even the bosonic version. So I think it's a good idea to test this method by comparing with our results for the bosonic model, because you have a solution for even for large matrix according to the Google researcher.
I don't have it. That is yet secret, and I didn't want to sign any agreements with them.
But if you can do that by yourself, if you can do the same thing by yourself, then you can easily compare.
No, I'm not doing that. This is impossible for me. You see, you could ask, why do the Google people do this? That is, they are interested in difficult problems that are well defined.
Okay.
And so their program apparently uses some machine learning and some artificial intelligence, and they have
I
a
see.
tremendous computer power. So there's no way how I can do that.
I see. I understand.
Yeah, no, but you're absolutely right. This is what I wanted to do, because if you have, I can even tell you what test you can do on your results that you got with Asato, for example, and with Costas, right? So if you have matrices of 64 by 64, then there are already lots of things you can test. Yes, and frankly, I am a little bit more optimistic that this equation is correct. That is because, I've worked on this 40 years ago, and this Eguchi-Kawai reduction at the beginning, and this is a very interesting idea. And quenching, I also understand very well. So I'm moderately optimistic, more than you.
Yeah, okay.
But we'll be in touch, right?
Yes, sure.
Okay, then if there's no other question here or online, then let's thank the speaker again. Thank you very much for interesting talk.
You're welcome.
Then as scheduled.
So is John still around there?
Well, I'm here, but
okay, good. Well, we now have a coffee break, John.
Okay,
so why don't you turn on your camera, and I can look at you.
Well, I cannot do that.
Oh,
here. I'm not allowed to do that, it seems.
Oh, okay.
Oh, sorry. Now I'm good.
Good.